Hey class, Adam Ward here. Second lecture recording here on form drag. We're going to spend this video looking at how fast we might move on a bike. And so before we do any calculations, just a thought experiment for us. So as you can see, beautifully illustrated here, a bicycle at the top of a hill. There I am riding, curly hair atop. And we're going to consider what happens if I ride this bicycle down the hill versus my daughter. Now, to keep it fair, I do have much longer legs than she does. She can't even reach the pedals on that particular bike. So let's assume we're not going to pedal. We're just going to go ahead and coast down here, right? So we'll pick our feet up and we're going to coast downhill to the finish line. And so the question is, which of us would reach the finish line first? And why would we reach that finish line first? So what I'd like you to do right now is think about this problem, think about the forces that are at play. Go ahead and hit pause and make your prediction. Okay, welcome back. Everybody's got a prediction in their mind. So, what are the forces at play here? One of those forces is drag. As I'm moving down the hill, my hair is being blown back by the wind. There is a drag force resisting my motion. And of course, we know the bigger that we make the cross-sectional area, so the frontal area, mine being larger than my daughter's, for example, the bigger that area, drag is going to go up and velocity is going to go down. But what's pulling me down the hill? Gravity. So the force of gravity is going to be the acceleration of gravity acting on the mass of the bike and the rider. So a higher mass, like myself, would accelerate faster, and that should increase my velocity. So, with those forces in mind, do you want to revise that prediction? You've got drag resisting, and you've got gravity pulling me downhill. Now, in both of those cases, I'm beating my daughter. I am both larger in cross-sectional area and substantially heavier in mass. So how do you know drag or gravity is going to dominate here? So take a moment to think about it, and then we'll talk. All right, so you've carefully assessed drag and gravity. You've got your answer. We know that area is a function of length squared. Right? So the cross-sectional area term in our drag coefficient is a length squared. The mass term associated with gravity, well, that's about the density of a human multiplied by the volume of a human. That's a function of length cubed. So because gravity is length cubed and area is length squared, or drag is length squared, we would expect that gravity will dominate in this problem and that I will actually win this race against my daughter, all other things being equal. So that was a bit of a thought experiment for us, and now I want to see how does this play out in predicting how fast one might actually go. Oh, then there's Happy Me down in the corner because I beat a child in a bike race that I contrived. All right, so we looked at a force balance in the previous lecture video for a grain settling. I'd like to do the same thing, but take a look at terminal velocity on a bicycle. Right, so let's assume a rider of 80 kilograms, a 10% grade on the road, and air at standard temperature and pressure. And so the question for you here is, what is going to be the terminal velocity of that cyclist? And in order to assess this, we need to do a force balance on that rider. And we'll assume that pulling me downhill is the downhill component of my weight. Right? So most of my weight force is going in the vertical, but some component of it is downhill, whereas some component is normal to the roadway. So shown in red, W sine theta, that's the downhill component of gravity. Resisting me, shown in green, is drag force. Now, why isn't drag force tipped? How come we don't have a sine or a cosine on there? We don't have it because we're actually analyzing forces along the surface parallel to the roadway. So we're not in a vertical coordinate system or a horizontal. Our coordinate system is going to be defined by that angle theta. All right. So gravity versus drag. And at my terminal velocity, as we talked about in the previous video, the gravitational forces pulling me downhill are going to come into balance with the drag forces that are resisting. In other words, mass times gravity times sine theta is going to be equal to that drag coefficient multiplied by 1/2 density of the fluid, velocity squared times area. And we can do the algebra to change this around so we can calculate terminal velocity. And let's go ahead and plug in some numbers. So up in the numerator, we've got the mass of the rider, 80 kilograms, gravitational acceleration, 9.81 meters per second squared, and we're multiplying that by the sine of theta. Now you'll notice I plugged in a value of about 0.01 radians. A 10% grade is approximately 0.01 radians. Right? And what a 10% grade strictly means is for every unit of 1 that you go to the left or to the right, you go 0.10 units up. So a 10% grade is approximately 0.01 radians. That's a calculation that you can confirm on your own. Down in the denominator, I'm taking the assumption that I'm going to be tucked down trying to be an efficient rider here. And so we'll use a drag coefficient of 0.9 and an area of 0.36 meters squared. And then you can see I've also plugged in the 1/2 and I've plugged in the density of air at 1.2 kilograms per cubic meter. Oh, sorry, the upright rider. Sorry, I did not. I am not tucking in and formally streamlined in this case. You're thinking of me going down a 10% grade. Right, so I picked the values for the upright rider, the slower rider in this case. Okay, so if we do this calculation, we would come up with a velocity of about 20 meters per second, and that translates to about 45 miles per hour. So what do you think? Is 45 miles an hour actually how fast you can go on a bicycle? 10% grade is a reasonably steep hill. If you're on the Indiana University campus here, that's about the steepness of Jordan Avenue as it goes by the library. So you might be moving along that road, but it's extremely rare for a cyclist to get up to 45 miles per hour. If you're going down that hill and you're going, let's call it 25 miles per hour, 30 miles per hour, that starts to get uncomfortable on a commuter bike for somebody heading through town. So 45 miles per hour seems like a pretty high bar. And the reason that we're predicting 45, right, we're thinking we might go faster than we would, is that we've missed some things. So there are forces besides drag that are resisting. For example, inside the bearings, there's friction in the bike. There is rolling resistance of the tires across the ground surface. So all of those little imperfections, every bump that you hit that slows you down, is going to affect that speed. So 45 miles per hour, is it a reasonable first cut if you didn't know anything better? Yeah, I suppose. But it shows us just how empirical or how limited those drag coefficients might be. So it did get us in the correct order of magnitude. If we were doing a quick calculation, is it plausible? This would be a good idea. If I was about to make a multi-million-dollar decision, I'd want to do some scale model testing before I would trust that rough estimate from a fluid textbook. So that's me on Jordan Avenue. Let's extend this line of logic just to one more sort of fun example. We're going to look at the land speed record on a bicycle. So let's pull this open. All right. So the land speed record on a bicycle is not set by someone, or at least at this time, this was land speed on a mountain bike, in fact. It's not set by somebody pedaling. In fact, it is set by somebody balancing and going downhill. And so this is truly the case we looked at, right? You're going down a very steep hill. You're going to tuck your body position, and we're going to try and see how fast can this rider go. And this is as close to our idealized case as I can find, where we've got gravitational acceleration pulling one way, and drag is the only thing slowing this person down. And so let's go ahead and watch what happens. So you're up on the top of a denuded mountain with a brave bicyclist. You can get a sense of just how steep that mountain is that this person is trying to bike down. Okay, so that's 163 kilometers per hour on the first attempt, which is just over 100 miles per hour, just to give you some context here. Second attempt, push off the top, getting up to about 100 miles per hour. And your the carbon fiber frame on your streamlined bicycle brakes at 100 miles an hour on a bike. Now, the rider does survive. We'll see in a moment here. He's looking pretty dazed, but he walks away and sets a mountain bike speed record for new mountain bike land speed record. Now, we're perhaps less interested in the speed record, but let's think about applying our force balance to this problem. So 163 kilometers per hour is approximately 110 miles per hour on a bicycle. That may be faster than, that's most likely, and if you're within the speed limit, definitely faster than any of us has gone in a vehicle, like a car, let alone exposed on a bike. That translates to about 49.2 meters per second. And so my question here is, based on our calculations, if you wanted to go 110 miles per hour on a bicycle, how steep of a mountain would you need to find? Certainly we know Jordan Avenue does not get you up to 110 miles per hour. And he didn't seem to be falling off of a perfectly vertical cliff. So how steep of a mountain does it take to go 110 miles per hour? All right, and you got a sense of that from watching the video, but we can actually calculate this value. So we'll take that same force balance that we started with, and let's go ahead and plug in these values. Now, we don't have the mass of that rider, but 80 kilograms is a reasonable estimate for an adult male. We've got gravity, 9.81 meters per second squared, sine theta, where theta is that unknown angle. And on the right, we're going to use the drag coefficient of 0.9 times 1/2. We got the density of air, 1.2 kilograms per cubic meter, our velocity squared, and a frontal area of about 0.3 square meters. And so if we go ahead and solve this out, it's an angle of about 30 degrees. And so here's just a quick animation for us of what does 30 degrees look like, right? That's about a third of the way through a 90 degree angle. I don't think that's too bad. Having watched that video several times for my own personal entertainment, I think it looks like that is probably a little shallow, meaning that the rider was on a hill that was a little steeper, right? So again, what happened? There's other places that energy is going in this video or in this scenario besides what we've considered. So in order to get up to 110 miles per hour, the friction in the bearings on that bicycle, for example, those are going to get hot, those are going to make noise, those are going to slow you down. And so 30 degrees is what it takes to offset drag. Any additional losses you have, like friction losses, for example, would require you get steeper to offset those. So 30 degree angle is what it takes to get over your drag forces, and anything else, rolling resistance of the tire, friction in the hubs, things like this, any other place energy goes would cause you to get steeper than that 30 degree angle. All right. So again, did we have a perfect assessment of this problem? It's unlikely. Did it provide a reasonable approximation of a real world situation? Yeah, I think it did, right? And so hopefully this is driving home to you all the idea that these empirical drag coefficients are averages, they're best fits to data sets, they're starting points, but they're often not perfect for any scenario. I hope that this helped you see how those drag coefficients might be used and get comfortable just working through a handful of examples where our force balance and all those different forces we've learned about, like hydrostatic forces, which generate the buoyancy, like gravitational acceleration leading to weight, drag forces now, all can come together in our sum of the forces problems to let us tackle external flows as well. All right, thanks for sticking with me all. That's our last video on form drag, and I will see you back for our next topic in a few days. Have a good one.